Okay, so this is section 6.1, and I'm dividing 6.1 into two videos. The first video will will uh, will outline the first three objectives: defining rational expressions, define rational functions and giving domains, and write rational expressions in lowest terms. So first off, we've got to define rational expressions. So a rational number, remember, is a quotient of two integers, right? And remember, the denominator cannot equal zero. So algebraically speaking, a rational expression is, or it's also called an algebraic fraction, is the quotient of two polynomials. And again, the denominator cannot equal zero because remember, if we have denominator equal to zero, we have division by zero. So here you can see examples of rational expressions. As it says, there are two polynomials, a quotient of two polynomials here. And a quotient, remember, means division. So what we have here, these are examples of rational expressions. And this is an introduction to this down here at the bottom is introduction to set builder notation, which we'll talk about here in a little bit. But notice that it says we have two polynomials, p over q. P and q are polynomials, and q cannot equal zero. That's a very important thing to remember about rational expressions, is that the polynomial in the denominator cannot equal zero. Otherwise, we would have division by zero, which is undefined. So we defined rational expressions. Now we want to get into functions and give their domains. So this is an extension on a little bit of what we've done in chapter 4, I believe, where we were talking about the domains of functions that had a fraction. So a rational function is defined as a quotient of polynomials. So again, we have something very similar to what we're talking about. We've got p of x over q of x. And remember, the function q of x cannot equal zero. So when we're talking about our domain of a rational function, that will include all real numbers except those numbers that make q of x, the polynomial in the denominator, equal to zero, because then we would have division by zero again. So looking at this right here, so we have a function here. We got f of z. Notice we've got z divided by z minus 11. So what this is talking about here is the values that make the denominator 0 must be excluded from the domain. If you remember from chapter 4, what we did was set the denominator equal to 0 and solve to find an excluded value. So, as it says here, to find each other, set the denominator equal to 0 and solve the resulting equation. So here we have it down here. We got z minus 11. We set it equal to 0. We add 11 to both sides. So 11 is an excluded value. Now, before, when we were representing domains, I guess this was in chapter 2, where we were representing domains, we used interval notation. And so this is how we represent the domain of a rational function with the excluded value here, with the parentheses negative infinity, comma, the excluded value 11 union the parentheses the excluded value to infinity. What that's saying is all real numbers except for 11. Now this notation right here is called set builder notation, which is what they say up here. Give the domain of each rational function using set builder notation and interval notation. So we've got it done in interval notation. We've done this before. What's new here is this set builder notation. So again, we have a set using the brackets around it. And the way that this is explained is the set of all z's bar, where z is a real number, z not equal to 11. So in interval notation, you put the excluded value, negative infinity to excluded value, union excluded value to infinity. In set builder notation, you identify what the excluded value is by putting z not equal to the excluded value. So big difference here. This is set builder notation. This is interval notation. So here we are. Give the domain of each rational function using set builder notation and interval notation. So looking at A, notice that 5 will never be 0. So in interval notation, the domain for this particular function is all real numbers, negative infinity to infinity. All real numbers, remember, represented in interval notation as negative infinity to infinity. Now, in B, this is an interesting case. Remember, we say what we do to find the excluded value is set the denominator equal to 0. So if we were to do this in this case, 5v squared plus 6, subtract 6, divide by 5. And if you remember from previous courses, the way to solve a squared equation is to take the square root of both sides. So if we take the square root of both sides, we get negative 6 fifths, square root of negative 6 fifths. Now, if you might want to try to put that into your calculator, it'll give you a domain error. So if you can't take the square root of a negative number. In chapter 7, we'll talk about how to deal with imaginary numbers. But right now, we're saying that this is not a real number. So there are no excluded values in this case because there's no way using real numbers that we can end up with a 0 in the denominator here. So in set builder notation, we would say the domain is negative infinity to infinity. And that's interval notation, I'm sorry. In interval notation, we would say it was negative infinity to infinity. In set builder notation, we would say V is a set of all V's where V is a real number. So in this particular case here, it's going to be all real numbers. Their domain is. So now we're going to look at objective 3. We're going to talk about writing expressions in lowest terms. So here's the fundamental property of rational numbers. So here we have a quotient, A over B, right? And if it's a rational number, and so let's say we have another number, C, non-zero real number, and we multiply that, we can actually cancel that C out. So what we have here down here below, notice we have 15 over 20. We can rewrite 15 as 3 times 5, and we can rewrite 20 as 4 times 5. Those 5s will cancel out, so this reduces down to 3/4 because 5 over 5 is 1. So this reduces down the 3/4. This is something that we've been doing since grade school, that is reducing fractions. We're just going to deal with reducing expressions in this particular objective. So here's the idea. To write irrational expressions in lowest terms, the first step is to factor both the numerator and the denominator to find their greatest common factor. The next thing we would do is apply the fundamental property and divide out common factors. Right now, this isn't going to make a whole lot of sense until we start looking at examples. So here's an example. So remember, the first step is to factor the numerator and the denominator. And we've talked about how to factor these things before. So if we look at this, let's go ahead and factor this. So we factored the numerator and we factored the denominator. Notice something about this, that we have a common term in both the numerator and the denominator. We have y minus 1 as a common term. So actually what we're going to do here is cancel those out. And what we have now is this expression written in lowest terms now. So y plus 3 over y minus 2. Once again, we canceled out the common factor. So looking at B, this one here, y squared plus 4 is a sum of squares. Remember, there is no special factoring formula for sum of squares, only difference of two squares. So this particular one in B is already in lowest terms. Now looking at C, what we have in the numerator is the sum of cubes, because 1 times 1 times 1 is 1, right? So we would use the sum of cubes formula here to factor the numerator, which is what we've done right here. What I really want you to pay attention to is that we have this 1 plus p common in both the numerator and the denominator. So that 1 plus p is going to cancel out. So now we have this trinomial, and it is written in lowest terms. Once again, we factored the numerator and the denominator, then we cancel out the common factors. So now we're going to look at A here. Notice something about A. If we were to factor out a negative 1 in the denominator, that creates r minus 1. So now we have r minus 1 in both the numerator and the denominator. And that simplifies to negative 1. All right? These are actually called opposites. And whenever they're written into a rational expression, they come out to be negative 1. So now looking at B, we got to factor this. And how we've factored is, first we've taken out a negative 1 out of the denominator. That creates p squared minus 4. Now p squared minus 4 is a special factoring situation because it is a difference of two squares. Remember that from section 5.3, p squared minus 4. So now what we have here in common in the numerator and the denominator is p minus 2. P minus 2 is in common, so that will cancel out. And so we're left with this as our simplified rational expression written in lowest terms. So here's the idea I was talking about in the previous example, is that you can have the quotient of opposites. So basically the idea here, looking at this one, q minus 7 over 7 minus q, these are actually opposites. Because if I were to factor out a negative 1 in the denominator, I would end up with q minus 7, and the q minus 7 would cancel out, and we would end up with negative 1 like we did in the previous example. And this is the same deal here. Notice if in the numerator here, if I were to factor out a negative 1, I would have negative 1 times 5a minus 2b in the numerator, and then I got 5a minus 2b. The 5a minus 2b would cancel out, and I would end up with negative 1. So what we have here are opposites. But what I do want to bring attention to here is that r minus, this example here, this final one here, r minus 2 over r plus 2, these are not opposites. they have to look something like these two examples. R minus 2 over R plus 2. These are not opposites, so it cannot be simplified further.